you. Thanks. Okay, yeah, this is working. Hi. So I'm Alice Pasetto, and I work in the Institute of Radio Astronomy and Astrophysics in Mexico, Morelia, in the campus, UNAM campus. So today I'm gonna show you, talk about polarization, a topic which has not been explored so far in this meeting. So let's see if I understood correctly. The green one. Yes, this one. Okay. So I'm gonna talk about two polarization property on two classes of object. One is the jet at kiloparsec scale of M87, and the second one is the class of object, the so-called compact symmetric object. So let's start with M87. And I don't want to make a long introduction, but just to say that searching for helical magnetic field first is a key ingredient for the formation and launching of jet in astrophysical object. And searching for helical magnetic field is possible through polarization, using polarization. Why? Using this, let's say, three key points. Searching for Faraday rotation measure gradient across the jet. We also should search for stratification of fractional polarization across the jet. And when is it possible, also a proper modeling of the polarized light. So radiopolarimetric studies have been very challenging, mainly for these two reasons I put here on the slide. First, we need high sensitivity observation because polarization information is just a small fraction of the total intensity. And up to since few years, we just got sparse and narrow band polarization. These make difficult to proper understand the behavior of polarization. Nevertheless, have made important and significant work here. I just cite this one from Zavala and Taylor, 2003, where they made a complete survey, measuring Faraday rotation measure on AGN at parsec scale. Okay, what do we need to study magnetic field configuration? Well, so high angular resolution transverse to the jet, so not along the jet, but to measure the angular resolution transfer to the jet, high sensitivity both in continuum and polarization intensity, and also high spectral sensitivity to follow the behavior of polarization properties. So the best instrument so far is the VLBI, is the best technique to investigate this topic because it gives us the best angular resolution. Nevertheless, it's very difficult because it is difficult to resolve its width and it collects sparse radio data. Here I show you two of the best cases we have right now. Is the 3C120 by José Luis Gómez, 2008, and Tavliki Ovata, 2012, on 3C273. They measure, as you see here, a gradient in rotation measure and a stratification of the fractional polarization. Let's see, the pointer is this one? No, this one here. Okay, yeah. This is the gradient of rotation measure and stratification of polarization. But as you can see, so the transverse resolution is what is missing. Okay, so VLA is another important instrument for such investigation. It measures, it traces different scale, kiloparsec scale, but nevertheless is very important because with VLA we can understand up to which scale the magnetic field is propagating. And plus the VLA has broadband receiver, which gives us high spectral sensitivity. So with these people here in the picture, I could work on new VLA observation on M87, and I want to show you this very pretty image of the total intensity map of M87 using Robust1, just to show you how good are the data. We could recover, start to recover the extended emission of the radial lobe of M87, but what now the results I'm focusing on are based on this image of total intensity map using uniform. So just to know, full polarization from CKU band observation, so from 4 to 18 gigahertz, and we are going to show, I'm going to show you the result of what I called the conical jet part, okay? So, and this is obviously the polarization image of M87. We performed the polarization modeling using each spectral window in the wideband, so 128 megahertz width. And we perform images of fractional polarization and polarization angle pixel by pixel. And here are the results. So we detect two filaments with a double helix in this conical jet part. Here are marked the knots. So from knot D and knot E, you can see these filamentary structures, which seem to be two different filaments intersecting each other. And here the polarization information in this conical jet part. Here you can see in color the fractional polarization, and under superimposed on the map in gray are the configuration of the magnetic field. So here you can see that the magnetic field follow pretty well the filamentary structure. You can see here high fractional polarization in yellow, and followed by darker area where there is a low fractional polarization, so depolarization mechanism. And if we zoom in, this is on the bottom, the map of the sign of the rotation measure. So this is in red is negative rotation measure, and blue is the positive rotation measure. So meaning that the rotation measure, the magnetic field is rotating towards the observer and away from the observer. So here we observe a synergy of the magnetic field with instability of the medium. So the question was why we see helical magnetic fields up to kiloparsec case. So that's the answer. Is a synergy between the Kelvin-Helmholtz instability and the helical magnetic field. So so we ask ourselves if this is a common feature. Well, we speculate that if other objects are seen with high resolution and high sensitivity, we can also see these features in other objects. So we got a new observation of 3C120, and I'm working with a student, Luca Ricci from Max Planck Institute, and we have CX and KU band full polarization UVLA data. So stay tuned for more information. So another topic, polarization on the compact symmetric object. I skipped the introduction, gave in the excellent work talk by Patil. Thank you very much. And I'm focusing on the polarization. So here's the introduction, our compact, symmetric, low polarization. So the interesting thing is that the nature of the compact symmetric object is still not clear, whether they are young radio sources or they have they are frustrated in a dense medium. So polarization can help, is a key tool to understand this, the nature of this, thank you, the nature of this object. And how? Studying the depolarization. Indeed, depolarization could be used to test the engulfed cloud model, which support the use scenario. So the engulfed cloud model is a model where the interstellar medium is engulfed by a cocoon and is photoionized by synchrotron UV emission from the lobe of the young AGN. So this process generates internal Faraday depolarization, and also could be also useful to see the free absorption in the radio spectrum. So we got 30 hours with ATCA, ATCA from 4 to 40 gigahertz for 8 CSO in the south, and 10 hours with the VLA from 4 to 12 gigahertz for our other 40 CSO. But thanks to Frank Schinzel, I got much more sources. So I have a total right now of 100 of CSO. But now Frank told me that there's more, so when I come home, I have much more work to do. So the idea is to characterize the magnetic and ionic environment of this object and understand this nature. So, but here just I want to briefly show you preliminary analysis, very preliminary analysis I've got. So data have been calibrated, analysis started after 6 years. So yeah, thank you for your patience, for the collaborators, I mean. Almost all the targets show the classical GPS spectrum. Most of them show a break at high frequency. So here in red is the classical synchrotron spectrum, and green is a synchrotron spectrum with a break at high frequency. And polarization have been clearly observed for roughly 15% of the sample, 13 targets. Still, I'm working on how show properly the data. There are scatters. I mean, at high frequency, the data have been much more noisy, but at the Stokes Q and U clearly cross each other. There is a depolarization going there, and but yeah, I need to still analyze better the data and perform the proper modeling. So this is my concluding slide. So the upcoming ngVLA and SKA, of course, will have the enough sensitivity and resolution to study the polarization properties of AGN jets. And these are just 3 of the topics that we can cover. We can perform complete 3D map of the magnetic field, explore the connection between instabilities and magnetic field in AGN, and explore how the jet evolved intrinsically and how they interact with the surrounding. And with this, I thank you very much for your attention.
All right, questions? Any questions online? All right, I see a few.
Hi, thanks. Well, comment and a question. The comment is, in terms of CSOs, there's been some recent work suggesting they might actually be due to tidal disruption events, which is an interesting hypothesis. The question is more on the helical magnetic fields. Is there a simple or quasi-intuitive picture of how the Kelvin-Helmholtz instability gives rise to the helical structure?
So, yeah. So, so regarding this, I mean, can you show me the extra slide I got? So for around 40, 48, something like that. Yeah, I'm sorry, I have a lot of extra slides. Go down. Yeah, 40. Okay, yeah. No, okay. Let's see. I can scroll down. Okay. So yeah, thanks. Yeah, so here we made a, how can I, okay. We studied the energetic of the jet. So we analyzed the energetic of the jet. So there is a model by Nakamura 2001 and Nakamura-Meyer 2004, where they study the alignment of the filaments with the magnetic field to explain this wiggle. But this, as I said here in the slide, you should need a magnetically dominated jet. So this up to 1 kPa scale. So this challenge this paradigm where the jet changes from magnetically to particle dominated jet. So we just repeat rapidly the energetic of the study of the energetic of the jet, and a lot of the work have been done, say by Lobanov 2003, where indeed the jet seems to be particle dominated. So this justify the interpretation of a helical magnetic field based on the Kelvin-Helmholtz instability. So the Kelvin-Helmholtz instability are produced from the disk, the accretion disk, and they magnetic field and instabilities, they feed each other and to stay visible until kiloparsec scale.
Okay, I saw a few other hands up. Sarah?
Hi, that was a great talk, thank you. And one of the earlier plots you had what looked like a kind of rotation measure versus distance from the center of the black hole, I guess the location of the black hole. And it looked like the rotation measure was falling off as you got further and further away. That must have been like an unresolved source, if I'm interpreting that right.
Okay.
My question is, why does the RM change as a function of distance from the dead? Is that straight due to electron density, or is it something else?
Yeah, I mean, rotation measure is integral of electron density, the magnetic field, and along the line of sight and the dimension. So as soon as you go out, away from the black hole, so the magnetic fields tend to be less intense, and you have a gradient of particles. So yeah, all that combination justify that you have a decrease also. You could have, because at some point of the jet you have also an increase of rotation measure. Like in knot A, we have detected an increase of rotation measure due to the shock front known shock front in knot A.
Okay. Yeah, I guess my underlying question was, can you disentangle those? Are you able to look at the profile and understand what's changing?
No, at the moment, no.
Okay, one more quick question, and then we'll have to save all others for Slack.
A great talk. So I have a question. So how many sources do we expect with SKA and ngVLA for studying polarization of helical magnetic field like M87?
I don't know, but lots more. I mean, for the moment, I just apply for this 3C 120 target. The other target I wanted to see was 3C 273 or 3C 279, I don't remember, because they show previous studies shown wiggles and filamentary structures and helical magnetic field sign. But yeah, now with ngVLA and SKA, we will have higher angular resolution. We can higher sensitivity, so we can go to detect fainter sources and the fainter structure of the jet. So our volume of knowledge of polarization of AGN will increase dramatically. So actually, yeah, I don't have this number now, but I want to see how much AGN will be discovered with these structures with the new ngVLA and SKA.
All right. We're out of time, so let's thank Alice again.
Thank you.